Now let's look at how we're going to perform our experiment. We're going to put our unknown liquid into a flask, and we're going to cover the flask with a piece of foil. The foil has a tiny hole in the top. The hole is already there, and the foil, it has to be really tiny, and we have a special thing to make it really small. Anyway, then you will take your flask and you will dunk it down into water, and you will boil the water. Okay, and after 10 minutes, your unknown will no longer be a liquid. As it warms, it will vaporize, it'll form a gas, and it will push all the air out the top, and your entire flask will be full of vapor, your unknown vapor. We need to have only our unknown molecules in here. That's why we give you extra unknown, so that you can push out all of the air. We need all the molecules to be the unknown. And by the way, don't let it bug you that I'm saying vapor instead of gas. For most purposes, they're the same. Usually you use the word vapor if something is normally a liquid, like you say water vapor, but water vapor is a gas. It's the same thing, so don't let that bug you. Okay, so after 10 minutes, what is the temperature of our gas inside the flask? Well, it's in boiling water, so we would expect it to be at 100 degrees Celsius, and that's the temperature we talked about earlier that you'll use. And we already converted that temperature to Kelvin. It's 373.2. Be sure to use those sig figs on your report sheet. Okay, next we need to know the pressure. And so we need to know the pressure of the gas in here. And you might think that it's higher than the pressure in the lab. I do have a barometer, and I'll measure the pressure in the lab. It would be higher than the pressure in the lab, because when you heat something, pressure goes up, except that there's a hole. And gas will leave through this hole until the pressure inside the flask is equal to the pressure in the lab. So the pressure is actually equal to the pressure in the lab, which is called a barometric pressure. And I will measure that and put that number on the board. I will put it on the board in millimeters of mercury, and you will need to convert it as well. But anyway, so that's pretty simple. Let me tell you another interesting thing about that and why this works the way that it does. It's called Avogadro's law. At the same temperature and pressure, equal volumes contain equal numbers of molecules. In other words, when those particles, they're in here, when they're leaving, it's kind of like the right number need to leave for the pressure to be the same as in the room. Another way to say that is if everybody in the lab, every lab group, had the exact same size of flask, by the time we got our temperature up to 100 C, everybody's flask would have the same exact number of molecules in it, even though some people have different size molecules, some people have different compounds. Anyway, it's interesting to me that the same number of molecules would be in everybody's flask. That's the way that works out. Anyway, next we've got the mass. We need to know the mass of the gas vapor that filled, we need to know what the mass is of that number of molecules. And when it's in the gas phase, it's not easy to get the mass. It's kind of like if you wanted to get your weight and you try to take your weight while standing in a swimming pool, your weight would come out lower. And it's because you're kind of buoyant. Your density is kind of similar to the density of the water surrounding you, so you don't really get a good measurement of your mass or your weight. The same thing with this. When you have a flask full of vapor, its density is similar to the surrounding air, so when you put it on the balance, you're not going to be able to detect the full weight. So what we do is we take our vapor and we cool it. And when we cool it, it condenses again. Oh, I see ours changed colors. Well, that doesn't really happen, but anyway, so once it condenses again, we can put it on the balance and weigh it. So we'll get the mass of the liquid condensate, and that is the mass that our vapor did have. Okay, so that's good. The last one is a little tricky too. You see, our flasks that we're using say 250 milliliters on them, so you might just think, oh, the volume is 250 milliliters, but it's not. These flasks are not meant to measure 250 milliliters all the way up to here. In fact, they're just an estimate of that anyway. So to get the true volume of the gas that it occupied, what we'll do is determine the true volume of this flask. And so after we do our 2 trials of, we'll do it twice, where we add the unknown, vaporize it, heat it for 10 minutes, cool it, weigh it, then we'll dump that into the waste container. We'll add more unknown, heat it, cool it, weigh it, dump it to the waste container. We'll do that twice, 2 trials. Then we'll add water. So this is a different step. Then we'll just add water to our flask. And when you add your water to the flask, you want to add water up to the very top. And so you want that water to occupy the entire space of your flask. Then you will take the mass of the water. You'll have the mass of your unknown flask, and you'll be able to determine the mass of water. So say that 267.17 grams of water fit in your flask. Well, how many milliliters of water is that? Well, the density of water is 1.00 gram per milliliter. And that's just 3 sig figs, because that number is not exact. At room temperature, it's good to 3 sig figs, but if I wanted 4 sig figs, it would be 0.9998 or something like that. So anyway, that just has 3 sig figs. So if I want to know my volume, I'll start with my mass here, and I'm going to convert to milliliters. And I'm putting in my density. Oh, well, I'm just dividing and multiplying by 1. I get the same number. Except, watch the sig figs. This has 3 sig figs, so I'm going to lose significant figures when I do this calculation. Okay, so be sure you drop down your sig figs once you use the density. Drop it down to 3 sig figs. So now I know how many milliliters of water fit in the flask. So how big is the flask? So what is my volume of my unknown vapor? Very good. And of course you'll need to convert that to liters for your calculation. So watch this. Be sure you get this exact calculation down and that you follow those steps so you'll get the right sig figs and stuff. Okay, that's the trickiest part. And then you just plug into that equation like we did before. Let's look at our tips. You're going to be graded on accuracy, and of course significant figures are part of that. So the first thing is to watch your sig figs. Be sure that you record the temperatures exactly how I told you with the right number of sig figs. And we just talked about the volume significant figures. You need to use the same flask for the entire experiment. Sometimes people try to set up the trial 2 while they're waiting around for trial 1, because you will be waiting around a little bit in this experiment. The thing is, if you use a second a different flask for trial 2. That different flask has a different mass and a different volume than your first one. And so you're going to do that whole thing with water twice. So it doesn't pay to set up the second one. Just stick with one flask and use it for the entire experiment. You need to make sure that you boil, and by boil, I mean big bubbles coming up to the top. When you boil water, you may notice, initially you might have some little bitty bubbles that stick on the sides. Those little bubbles are not boiling. That is not water vapor. The first thing that happens when you heat water is that air comes out of solution. And so that's what you see, those tiny little bubbles. Boiling, like a rolling boil, I mean lots of bubbles coming to the top for 10 minutes. And the reason this is so important is that you need to make sure all of your liquid is vaporized. The problem is that you cannot look in that flask and see if there's liquid left in the liquid phase. It's very hard to really detect that. But we know for our unknowns that 10 minutes is long enough to completely vaporize them. Why must they be completely vaporized? What would be wrong if you went to the next step and there were a few drops of liquid left in the bottom? Well, when you go to the next step, you're going to have too many molecules in there. Remember we talked about the right number of molecules need to be left in there? Also, when you go to the next step, you're getting ready to apply gas laws. Gas laws don't work with liquids. Okay, so if it's all a gas, there are going to be fewer molecules in there. These extra, the liquid, will make your mass of your liquid condensate come out too high. And since that's on the numerator of your calculation, since mass is up here, if this number is too high, then your molar mass will come out too high. Okay, last tip here. Be sure to dry your foil quickly before you weigh your condensate. The foil wrapper will get wet, and it will even get liquid up underneath it. So you'll need to kind of pull it out straight. You'll need to kind of pull it out straight so that you can dry underneath it with a paper towel. The liquid water on the outside, again, would make this mass too heavy, and that can really throw things off. The amount of liquid condensate that you should have is about 1 milliliter, and so just a few drops of water can really throw that off.